Good morning, students. This is Arvind, Assistant Professor, Department of DBS Talks. So in the previous class, I discussed about variable impedance types static series compensators. In that class, I discussed about the one method that is GCSC, and now in this class, I am going to cover the remaining two methods, that is the TCSC and TSSC concept in this class. Okay. So firstly, I will start with the thyristor switch series capacitor, that is TSSC. Okay, thyristor switch series capacitor, that is known as TSSC in shortcut. So here I am taking the basic circuit arrangement of the TSSC, that is a thyristor switch series capacitor, that is shown in this diagram. This is the basic thyristor switch series capacitor scheme. So here I am taking bank of thyristor valves, that is known as switches, in this manner. Okay, so here I am taking M1 to M basic thyristor series capacitor scheme. I am taking, so it consists of the M capacitors and M thyristor valves. Okay, and we have voltage across these is VC1, VC2, and so on, VC minus 1 and so on, VCM, like that we are having. Okay, and we have the line current, that is I. Okay, so actually the circuit consists of number of capacitors. Okay, so if you observe the diagram, you will understand. Okay, it consists of number of capacitors, that is C1, C2, and so on, Cm minus 1 and Cm, like that. Okay, so it consists of a number of capacitors, each shunted by an appropriately rated bypass valve. Okay, each shunted by an appropriately rated bypass valve, that is the thyristor valves of switches, these things. So here I am taking two thyristors, both are parallel to each other. Okay, and this one is connected to parallel to the capacitors. Okay, so that's why I am telling that it consists of a number of capacitors, each shunted by an appropriately rated bypass valve composed of a string of reverse parallel connected thyristors in series. Okay, so as seen, it is similar to the circuit structure of the sequential of the GCSC. So in the previous class, I discussed about the GCSC concept. In that one, I will shown one diagram. So this one. So here, same diagram I am taking, but in a different manner. Okay. So as seen, it is similar to the circuit structure of the sequentially operated GCSC as shown in the previous class, but its operation is different due to the imposed switching restrictions of the conventional thyristor valve. Due to the imposed switching restrictions of the conventional thyristor valve. Okay, so that means the operating principle of the TSSC is straightforward. That is, the degree of series compensation is controlled in a step-like manner by increasing or decreasing the number of series capacitors inserted. Okay, so a capacitor is inserted by turning off, and it is bypassed by turning on the corresponding thyristor valve. Okay, so a capacitor is inserted by turning off, and it is bypassed by turning on the corresponding thyristor valve, that is switch. Okay, thyristor valve commutates naturally. That is, it turns off when the current crosses zero. I already said this point number of times in the previous class. Okay, thyristor valve commutates naturally. That is, it turns off when the current crosses zero. Okay, and thus a capacitor can be inserted into the line. Okay, thus a capacitor can be inserted into the line by the thyristor valve only at the zero crossing of the line current. Okay, at that time only we have to insert the capacitor into the line. Okay, next, so since the insertion takes place at line current 0, so at one position the line current crosses 0, that means the insertion of the capacitor takes place. That means at that time a full half cycle of the line current will charge the capacitor from 0 to maximum. Okay, a full half cycle of the line current will charge the capacitor from 0 to maximum and successive, and opposite polarity half cycle of the line current will discharge it from maximum to 0. Opposite polarity means, so in the first polarity we have the we have charged the capacitor from 0 to maximum. In the opposite polarity of off cycle of the line current, it will discharge it from maximum to 0. That is illustrated in this diagram. So this diagram gives the illustration of capacitor offset voltage resulting from the restriction of inserting at 0 line current. So here the switch is allowed to turn on at Vc is equal to 0. Okay, so here I am taking the graph. So actually it is in the sinusoidal manner. Okay, for that one I am taking this circuit. So this circuit consists of one capacitor and it is parallel with the thyristor valve, that is also known as switch, and it consists of the voltage across the capacitor and the line current. Okay, so here the first waveform gives the first sinusoidal, pure sinusoidal waveform gives the line current value, and when the switch is on, the voltage waveform is changed like this. So up to 1/2 cycle it comes as constant line, and after that it will decrease only in the negative direction. Okay, so at Vc is equal to 0 and Vc is equal to 0, we have the dotted lines. I am representing with the dotted lines waveform, sine wave. Okay, so that is, as can be seen, the capacitor insertion at line current is 0. Okay, that is necessitated by the switching limitation of the thyristor valve. Okay, that is necessitated by the switching limitation of the thyristor valve that results in a DC offset voltage. The DC offset voltage which is equal to the amplitude of the AC capacitor voltage. So which is equal to the amplitude of the AC capacitor voltage. Okay, so in order to minimize the initial surge current in the valve and the corresponding circuit transient, the thyristor valve should be turned on for bypass only when the capacitor voltage is 0. Okay, in order to minimize the initial surge current in the valve and the corresponding circuit transient, the thyristor valve should be turned on for bypass only when the capacitor voltage is 0. So this is the circuit and waveform for that explanation. And with the freewheeling DC offset, this requirement can cause a delay of up to 1 full cycle. Okay, with the freewheeling DC offset, this requirement can cause a delay of up to 1 full cycle. So which would see the critical limit for the attainable response time of the TSSC. Okay, and the TSSC can control the degree of series compensation by either inserting or bypassing the series capacitors, but it cannot change the natural characteristic of the classical series capacitor compensated line. Okay, actually the TSSC can control the degree of series compensation, that is by either inserting or bypassing series capacitors, but it cannot change the natural characteristic of the classical series capacitor compensated line. So this means that a sufficiently high degree of TSSC compensation could cause subsynchronous resonance just as well as an ordinary capacitor. Okay. So in principle, the TSSC switching could be modulated to counteract subsynchronous oscillations. Okay, in principle, the TSSC switching could be modulated to counteract the subsynchronous oscillations. That means, however, considering the relatively long switching delays encountered, the modulation is likely to be ineffective. If the modulation is likely to be ineffective because of the delay, long switching delays, and it's not counterproductive except for the very low end of the subsynchronous frequency band. So therefore, the pure TSSC scheme of figure 6.10 would not be used in critical applications. Okay. So this one. Okay, therefore the pure TSSC scheme of figure 6.10, that is, would not be used in critical applications where a high degree of compensation is required. Okay, where a high degree of compensation is required and the danger of subsynchronous resonance is present. Okay, so the pure TSSC scheme would not be used in critical applications where a high degree of compensation is required and the danger of synchronous resonance is present. So nevertheless, the TSSC could be applied for power flow control and for damping power oscillation where the required speed of the response is moderate. Okay. So the basic VA characteristic of the TSSC with 4 series connected compensator modules operated to control the compensating voltage that is shown in this diagram. So this one, in this one the first diagram, that is A1 diagram, gives the VA characteristics of the TSSC when operated in voltage control. That is for the first one, A1. Okay, in that one, for this compensating mode, the reactance of the capacitor banks is chosen so as to produce on the average the rated compensating voltage, that is VC maximum is equal to 4 into XC I minimum. Okay, for this explanation is for the first A1 diagram. Okay, in the face of decreasing line current over a defined interval, that is I is in between I minimum to I maximum. So the I, there is a line current is in between minimum current to maximum current. Okay, so as the current, that is I minimum, is increasing towards I maximum, the capacitor banks are progressively bypassed by the related thyristor valve to reduce the overall capacitor reactance in a step-like manner and thereby maintain the compensating voltage with increasing line current. Okay, so this is the explanation for the first, that is the A1 diagram. And next, so the loss as percentage of the rated wear output that is shown in this A2 diagram, that is below to the A1 diagram, that are loss versus current diagrams. We have wear output diagram versus line current characteristic of the TSSC operated in the voltage compensating mode, that is shown in the A2 diagram for zero voltage injection and for maintaining maximum rated voltage injection. Okay. So this is the explanation for the A2 diagram. That means maximum rated voltage injection means capacitors are progressively bypassing. So in the impedance compensation mode, so that is I am discussing about this B1 diagram. Okay, B1 diagram and explain. So in the impedance compensation mode, the TSSC is applied to maintain the maximum rated compensating reactance, that is excess at any line current up to the rated maximum, that is illustrated in the B1 diagram of this VA characteristic. That is the VA characteristics of this one. So that is B1, reactance control. Okay, A1 is the voltage control and B1 is the reactance control. Okay, so in this compensation mode, the capacitor impedance is chosen so as to provide the maximum series compensation at rated current, that is 4XC, that is equal to VC maximum by I maximum. So that means that the TSSC can vary in a step-like manner by bypassing one or more capacitor banks. Okay, so next I am discussing the last diagram of this VA characteristics and losses versus line current characteristics, that is in P2. So in this one, the loss versus line current characteristics for this compensation mode is shown in the figure, that is B2. For zero compensating impedance, at that time all capacitor banks are bypassed by the thyristor valves, and for maximum compensating impedance, at that time all thyristor valves are off and all capacitors are inserted. Okay, so for that one, the maximum rated line current and corresponding capacitor voltage are design values for which the thyristor valve and the capacitor banks are rated to meet the specific application requirements. Okay, so the TSSC may also have transient ratings, usually defined as a function of time. Those transient ratings will be usually defined as function of time. And outside the defined ratings, the TSSC would be protected against excessive current and voltage surges either by external protection across the capacitor and the parallel valve or with the sufficient rating by the valve itself in bypass operation. So outside the defined ratings of TSSC, we are taking protection for the TSSC That is for the against excessive current and voltage surface either by external friction. Okay, and constraints imposed by physical device limitation and the unknown conditions of thyristor, such as change in time, that is dI by dt in surge current magnitude, would necessitate in practice the use of current limiting reactor in series with the TSSC valve to handle bypass operation. So here I am taking the current limiting reactor in series with the TSSC. This will handle the bypass operation or possible misfirings which would turn on the valve into a fully charged capacitor of over 2 per unit voltage. Okay, and however, if reactor in series with the valve is included in the TSSC structure, then as explained in the next section, that is in the TCSC scheme, that is which can significantly improve the operating and performance characteristics of the series compensator. Okay, so this is the explanation for the first one, that is a TCSC, and next we are moving to the TSSC, and then we are moving to the TCSC scheme, and we are moving to the TCSC scheme. So in the TCSC scheme, actually the TCSC scheme proposed in 1986 by with other as a method of rapid adjustment of network impedance. Rapid adjustment of network impedance, that is shown in this diagram. So this one, so this is the basic thyristor controlled series capacitor scheme. Okay, this is basic thyristor controlled series capacitor scheme. So in this scheme, I am taking one thyristor valve that is known as switch, and it is connected to the reactor, and it is connected to the capacitor. So in this one, the capacitor consists of the voltage across the capacitor at delay angle alpha, and it consists of the capacitor current, that is IC of alpha is equal to I plus IL of alpha. So why? Because here we are using the reactor. That's why I am telling in the previous concept, that is a TSSC concept, I am taking a external reactor for the production because of the misfiring and any other cases we are taking that one. So that is included in this operation. That is a TCSC scheme. Okay, here I am taking the reactor. It consists of the current, that is ILF of alpha. Then it consists of line current. So that means from the diagram, it consists of the series compensating capacitor shunted by a thyristor controlled reactor. So in the practical TCSC implementation, several such basic compensators may be connected in series to obtain the desired voltage rating and operating characteristics. Okay, in a practical TCSC implementation, several such basic compensators may be connected. That is a connection of the reactor and the capacitors. Okay, in a practical TCSC implementation, several such basic compensators may be connected in series to obtain the desired voltage rating and operating characteristics. So this arrangement is similar in structure to the TSSC. There is a previous method, same arrangement, but if the impedance of the reactor, that is XL, is sufficiently smaller than that of the capacitor, that is XC, so XL is less than XC, then it can be operated in a on or off manner like the TSSC. Okay, so next, so however, the basic idea behind the TCSC scheme is to provide a continuously variable capacitor. So the basic idea behind the TCSC scheme is to provide a continuously variable capacitor by means of partially cancelling the effective compensating capacitance by the TCR. So this TCR is used in the previous chapter. There is a shunt compensation. So it is similar to the compensating capacitance of the TCR in the previous concept. So since as shown in the shunt compensation concept, the TCR at the fundamental system frequency is a continuously variable reactive impedance and controllable by delay angle alpha, and the steady state impedance of the TCSC is that of a parallel LC circuit consisting of a fixed capacitive impedance, that is XC, and a variable inductive impedance, that is XL of alpha. That is, I am writing X suffix TCSC of alpha is equal to XC into XL of alpha by XL of alpha minus XC. So From the equation that is 5.5, I am taking XL of alpha is equal to XL into pi by pi minus 2 alpha minus sin alpha, comma XL. In this case, the XL of alpha is in between XL to infinity. So these two equations are treated as 6.10 and 6.11. So if we take XL is equal to omega L and alpha is the delay angle measured from the crest of the capacitor voltage are equivalently the zero crossing of the line current. So at that time the TCSC presents a tunable parallel LC circuit to the line current, that is I. So that is substantially a constant alternating current source. Okay. So as the impedance of the controlled reactor, that is XL of alpha is varied from its maximum towards its minimum, that is infinity to omega L, the TCSC increases its minimum capacity impedance, that is X of its TCSC minimum is equal to XC, that is equal to 1 by omega C. So until parallel resonance at Xc is equal to XL of alpha is established and X TCSC maximum theoretically becomes infinite. So decreasing this XL of alpha, further the impedance of the TCSC, that is X of its TCSC of alpha, becomes inductive, reaching its minimum value of XL into XC by XL minus XC at alpha is equal to 0, where the capacitor is in effect bypassed by the TCR. So therefore, with the usual TCSC arrangement, in which the impedance of the TCR reactor, that is XL, is smaller than that of the capacitor, that is XC. So the TCSC has two operating ranges around its internal circuit resonance. That is, one is the alpha C limited, that is less than or equal to alpha less than or equal to pi by 2. In this one, the delay angle alpha is in between alpha C limited to pi by 2 range, where X TCSC of alpha is capacitor, and other, that is the second one, is the, in this one the alpha is in between 0 to alpha L limited range. So in this one X TCS of alpha is inductive, that is illustrated in the diagram, that is this diagram. So this diagram gives the impedance versus delay angle alpha characteristic of the TCSC. Okay, so in this one I am taking the circuit arrangement. There is the basic general scheme of the TCSC. Okay, so this is the connection diagram I am taking. So based on this diagram I am taking the impedance versus delay angle characteristics of the TCSC. So in this one the characteristic diagram, in the characteristic diagram the above waveforms gives the characteristic diagram gives the inductive manner of this TCSC, and the below this one gives the capacitive characteristic of the TCSC. So here the inductive region, the resonance, that is XL of alpha is equal to XC. In this one operation I indicated for alpha is in between alpha limited to alpha C limited. Okay. And in the left side we have the inductive region, and on the right side we have the capacitive region. So the inductive region is in between alpha from 0 to alpha L limited, and the capacitive is in between alpha, that is alpha C limited to pi by 2 range. Okay, here the alpha is in between 0 to pi by 2. So next, here I am taking the steady state model of the TCSC described above is based on the characteristic of the TCR, that is established in an STC environment. That is, STC is the static charge generator type, that is STC, static charge compensator environment. I am taking, this is in the last chapter. So where the TCR is separate from a constant voltage source. The TCR is separate from a constant voltage source. So this model is useful to attain a basic understanding of the functional behavior of the TCSC. So, however, in the TCSC scheme, the TCR is connected in shunt with the capacitor. The TCR is connected in shunt with the capacitor instead of a fixed voltage source. So in the fixed voltage source place we are connecting TCR in shunt with the capacitor. So the dynamic interaction between the capacitor and reactor changes the operating voltage from that of the basic sine wave established by the constant line current. So a deeper insight into this interaction, that is the interaction of the TCR in connection with the capacitor. So a deeper insight into this interaction is essential to the understanding of the actual physical operation of the and dynamic behavior of the TCSC. So particularly regarding its impedance characteristic at subsynchronous frequencies. So refer to the basic TCSC circuit. Refer to the basic circuit that is in the 6.13. So this one, refer to this diagram. Okay, refer to this diagram. For convenience, is also shown at the top of figure, that is this one, 6.15. B, that is this one. Here I am adding the switch and the diode. Okay, so in the first diagram, in the B diagram we have two diagrams, two arrangements. In the first arrangement we are taking the TCSC, but in the second we are taking which one? That is equivalent circuit of the TCSC at the firing instant alpha. Here I am taking diode and switch and inductor and capacitor like that. So from this one, so refer to the basic TCSC circuit that is shown in the previous slides. For the convenience is also shown at the top of the figure, that is the same diagram I am taking for this one. But assume that the thyristor valve, that is switch, is initially open and the freewheeling line current I produces voltage, that is VC naught, across the fixed series compensating capacitor that is illustrated in the A diagram, that is this one. So here we have I, that is the line current, and we have the VC naught. So this VC naught is produced initially opening the switch. At the time the line current is produced as the VC naught across the fixed series compensating voltage, that is VC naught, that is the this one. Okay, there is a diagram of this one. And next, suppose that the TCR is to be turned on at a measured from the negative peak of the capacitor voltage. Suppose that the TCR is to be turned on at alpha, that is measured from the negative peak of the capacitor voltage. So the diagram is shown like this, that is the C diagram. Okay, the C diagram gives the resulting capacitor voltage and related TCR current. Okay. So this is the basic thyristor control scheme for the capacitor scheme. Already I discussed this one. And next, so as seen that at this instant of turn on, the capacitor voltage is negative. So the line current is positive. So when the turn on, the capacitor voltage is negative and the line current is positive, and thus charging the capacitor in the positive direction. And during the first half cycle, that means all similar subsequent half cycles of TCR operation, the thyristor valve can be viewed as an ideal switch. Okay, the thyristor valve can be viewed as an ideal switch closing at alpha in series with the diode. That is, I am explaining about the B diagram. So in the B diagram we are taking one diode and switch, and this switch is connected to the reactor, and this reactor and diode is connected to the capacitor in the diagram. So during the first half cycle of TCR operation, the thyristor valve can be viewed as an ideal switching, that is closing at alpha in series with a diode of appropriate polarity to stop the conduction as the current crosses zero. That is as shown in the bottom of figure, that is 6.15 B diagram, that is the bottom of the B diagram. So at the instant of closing switch, so two subsequently independent events will take place. So instant of closing the switch, that is I am explaining about the B diagram. Okay, so two substantially independent events will take place. One is that the line current being a constant current source, the line current that is I, that is being a constant current source, continues to charge or discharge the capacitor. So the other one is, that is the second one is that the charge of the capacitor will be reversed during the resonant half cycle of the LC circuit formed by the switch closing. Okay, that is the second event assumes that XL is less than XC. That means the resonant charge reversal produces a DC offset for the next half cycle of the capacitor, that is positive voltage, that is shown in the C diagram, that is this one. So this diagram, C diagram. Okay, so So in the subsequent half cycles, the DC offset can be reversed by maintaining the same alpha, and thus a voltage waveform symmetrical to the zero axis can be produced. That is shown in this diagram, that is 6.16. So this diagram gives the capacitor voltage, that is DC, and current waveform, that is I, together with the TCR voltage and current waveform, characterizing the TCSC in the capacitor region under steady state operation. Okay, this is the waveforms I am taking. So in this one, the relevant current and voltage waveforms of the TCSC operated in the capacitor region. Okay, the relevant current and voltage waveforms of the TCSC operated in the capacitor region. So this one. So similar waveforms are shown for the inductive operating region. So this is for the capacitor region, and next I am showing the inductive region. Okay. So these waveforms for the inductive region. Okay. So in this one, the reversal of the capacitor voltage is clearly the key to the control of the TCSC. The reversal of the capacitor voltage is clearly the key to control of the TCSC. So the time duration of the voltage reversal is dependent primarily on XL by XC ratio, but also on the magnitude of the line current. So if XL is less than XC, then the reversal is almost instantaneous, and the periodic voltage reversal produces a square wave across the capacitor that is added to the sine wave produced by the line current. Okay, so that is the expression for this one, for the inductive region, and thus as illustrated in figure 6.18. So this one, so in this one I have taken the comparison of the idealized TCSC compensating voltage waveform from the line current produced capacitor voltage and the square wave voltage generated by the capacitor voltage reversal. Okay, so in this one, the steady state compensating voltage across the series capacitor compresses an uncontrolled and a controlled component. So that means the uncontrolled component is VC naught. So in this one, the uncontrolled component is VC naught, that is in the pure sine wave in the first diagram. In the first waveform, we have VC naught. This is a completely sinusoidal wave, a sine wave whose amplitude is directly proportional to the amplitude of the prevailing line current. That's why I am taking the dotted lines waveform, that is I. This VC naught is prevailing to the current I. Okay, and the controlled component is VC TCR, substantially a square wave. So here I am taking the second one, that is square wave, that is VC TCR. That is the voltage across the capacitor at TCR. Okay, it is substantially a square wave whose magnitude is controlled through charge reversal by the TCR. Okay, so for a infinite but still relatively small, that is XL, the time duration of the charge reversal is not instantaneous but is quite well defined by the natural resonance frequency, that is F is equal to 1 by 2 pi root LC of the TCSC circuit. Since the TCR conduction time is approximately equal to the half period corresponding to this frequency, that is T by 2, that is equal to 1 by 2F, that is equal to pi into root LC. That is the half period of the corresponding frequency, that is F is equal to 1 by 2 pi root LC. That will convert into T by 2, that is equal to 1 by 2F, that is equal to pi into root LC. So however, as XL is increased relative to XC, that is XL is greater than XC, the conduction period of the TCR increases and the zero crossing of the capacitor voltage become increasingly dependent on the prevailing line current. So it should be noted that the impedance of the TCR reactor does not significantly alter the physical operation of the TCSC, provided that it is sufficiently small in relation to the impedance of the capacitor to facilitate the desired control of the series compensation. So however, the design of the reactor for an actual compensator requires careful considerations to reconcile contradictory requirements. So on the one hand, small XL is advantageous in providing well-defined charge reversal and control of the period time of the compensating voltage. A small reactor is also advantageous in facilitating an effective productive bypass for large surge current encountered during the system faults. So on the other hand, small XL increases the magnitudes of the current harmonics generated by the PCR and circulated through the series capacitor, and thus also increase the magnitudes of the capacitor voltage harmonics injected into the line. So after we discussed about the operation of this TCSSC, and now we are moving to the harmonic concept in the TCSC. So that means it also decreases the range of actual delay angle control, and thus possibly makes the closed loop parameter regulations more difficult. So in addition, small XL produces large short circuit current pulses in the thyristor valve. So small XL produces large short duration current pulses in the thyristor valve, necessitating the increase of its current rating and possibly also its voltage rating. So in present installation, the XL by XC ratio used is 0.1. This is the prototype, and thus the national resonant frequency of the TCSC circuit is 2.74 times the 68 fundamental frequency. So generally, the XL by XC ratio for practical TCSCs would likely be in 0.1 to 0.3 range. So depending on the application requirements and constraints, so it is important that the natural resonant frequency of the TCSC does not coincide with or is close to 2 and 3 times the fundamental. Okay, so the mechanism of controlling the DC offset by charge reversal is illustrated for increase and decrease of the capacitor voltage in the two diagrams, that is 6.19A and 6.19B. So in these two diagrams, I am giving the mechanism of controlling the DC offset by charge reversal is illustrated for increase and decrease of the capacitor voltage. For the clarity of illustration, theoretically, ideal case of instantaneous voltage reversal is assumed. So, for the clarity of illustration, the theoretically ideal case of instantaneous voltage reversal is assumed. So, I am explaining about this diagram, that is 6.19A. In this one, I am increasing the capacitor voltage by advancing the voltage reversal from alpha is equal to pi to alpha is equal to pi minus theta. Okay. So in figure 6.19a, so in this one, initially TCR is gated on it alpha is equal to pi by 2. In this one, the TCR is gated on it alpha is equal to pi by 2. Okay. At which the TCR current is 0. So in this one, so if you observe the third diagram, in this one the TCR current is 0, therefore we don't have any waveform. Okay, up to pi. Okay, so 0, and the capacitor voltage is entirely due to the line current. So here the capacitor voltage is entirely due to the line current, that is in the first diagram. So in the first diagram we have the sinusoidal waveform, that is for the line current. So depending upon the line current, the capacitor voltage is varying. Okay, that is the last diagram. So to produce a DC offset, the periodically repeated gating in the second cycle is advanced by a small angle epsilon, that is the prevailing half period is reduced to epsilon to pi minus epsilon. So that is alpha is equal to pi minus epsilon, that is this one. So alpha is equal to pi by 2 and pi, and next pi minus alpha, and next pi plus epsilon, and we have pi. Like that we are having the PCR current and PCR getting controlled. Okay, so next, so this action produces a phase advance for the capacitor voltage with respect to the line current, and as a result the capacitor absorbs energy from the line, charging to a higher voltage. So should this phase advance should be maintained, then the offset charge of the capacitor would keep increasing its charge at every half cycle without theoretical limit, as usually for the subsequent half cycle in the diagram, that is this one. Okay, there is a TCR getting control. So however, if the epsilon phase advance is negated, so when the sufficient offset level of the capacitor voltage is reached, so then the capacitor voltage at the desired magnitude can be maintained by continuing periodic gating at the line current zeros, that is alpha is equal to 0, as shown in the successive half cycles in this 6.19 diagram. Okay, that is a pi like that we are taking the gating controls. Okay. And next coming to the B diagram, that is this one. Okay, in this one also same explanation. So in this one, decrease of the capacitor voltage. So previously I am increasing the capacitor voltage, that is the 6.19 A diagram. So in the 6.19 B diagram, I am decreasing the capacitor voltage by recording the voltage reversal from alpha is equal to pi to alpha is equal to pi plus alpha. So in the previous class I am taking pi alpha is equal to pi to alpha is equal to pi minus epsilon. Now in this one I am taking alpha is equal to pi to alpha is equal to pi plus epsilon. Okay. So in figure 6.19b, the opposite process is illustrated, that is from the A diagram, the opposite process is illustrated, that is when the magnitude of the capacitor voltage is decreased by retarding the periodic gating from the current zeros until the desired offset voltage level is reached. So with a practical TCR, the voltage reversal will take place over a finite conduction period, that is sigma, and this period would vary with the applied phase advancement or retard, and the circuit would behave as if a conventional delay angle control was applied. Okay. So the process of transition from one capacitor voltage to another therefore will be more complex than the theoretical case illustrated. So it would be a function of the prevailing line current, and generally there would be a transitional period before a steady state condition would be reached. So however, the end result would be substantially the same. So from those two diagrams, it has been shown above that the original objective of providing continuously variable series capacitor compensation can be achieved by the TCSC circuit structure. So that is, the effective capacitive impedance of the TCSC can be increased above the actual reactance of the capacitor band by increasing the conduction angle of the TCR. So this increase of the effective impedance is due to the additional voltage the TCR produced across the capacitor by the repetitive charge reversal. So from the qualitative circuit analysis provided, this process can be summarized in the following way, that is, firstly, when the thyristor valve of the TCR is gated on, okay, when the thyristor valve of the TCR is gated on prior to a negative to fast zero crossing of the capacitor voltage, that is dVc by dt is greater than 0. So at that time the prevailing capacitor voltage will drive a current in the TCR, okay, that will self-commutate when the integrated volt seconds over the conduction interval becomes 0. So then the current in the reactor is supplied from the parallel capacitor. Okay, the current in the reactor, that is from the TCSC, the current in the reactor is supplied from the parallel capacitor. So thus the capacitor voltage will change in proportion to the integral of the reactor current. So that is reversing its polarity by the end of the conduction period, So this positive voltage offset will remain until reversed again by a similar TCR conduction period around the positive to negative zero crossing of the capacitor voltage, that is dVc by dt is less than 0 in the subsequent half cycle. So the periodic reversal of the offset voltage adds a controllable in-phase alternating voltage to the uncontrolled capacitor voltage produced by the line current. So in this way, the TCSC can increase the compensating voltage over that produced by the capacitor bank along at a given line current. So in other words, the TCSC can increase the effective impedance of the series compensating capacitor. Okay. So that it is important to appreciate that in contrast to the TCSC, the GCSC controls the capacitive impedance from 0 to the actual impedance of the capacitor. Okay, it is important to appreciate that in contrast to the TCSC, the GCSC controls the capacitive impedance from 0 to the actual impedance of the capacitor. So the compensating voltage versus line current characteristic of the basic TCSC is shown in the 6.20, that too from the A1 diagram. Okay, so these four diagrams gives the attainable VI characteristics of the TCSC when operated in voltage control and reactive control modes and the associated loss versus line current characteristics. That is A1 and B1 gives the associated compensating voltage versus line current characteristics, that is VI characteristics of when operated in voltage and reactance control, and the A2 and B2 gives the associated loss versus line current characteristics. Okay, so that is, so as illustrated in the capacitive region, the minimum delay angle alpha C limited sets the limit for the maximum compensating voltage up to a value of line current, that is I minimum, at which the maximum rated voltage, that is VC maximum, constrains the operation until the rated maximum current IC maximum is reached. Okay, so that is for the A1. Next, in the inductive region, so after we discussed the capacitive region, so in the inductive region, the maximum delay angle, that is the alpha limited, limits the voltage at low line currents and maximum rated resistor current at high line current. Okay, it limits the voltage at low line current and the maximum rated resistor current at the high line current. So that means the loss, that is, I am explaining about the A2 diagram, the loss as a percent of the rated VAR output versus line current for voltage compensation mode in the capacitive operating region is shown in the A2 diagram, that is this one. There is a loss versus characteristic line current diagram. Okay, so it is for maximum and minimum compensating voltage. It is for maximum and minimum compensating voltage as well as for bypass operation, Here we are considering the XC minimum, XC maximum and VC minimum, and VC is equal to 0. Okay, so the losses are almost entirely due to the TCR. The losses are almost entirely due to the TCR, that is thyristor control reactor. So which include the conduction and switching losses of the thyristor valve and the I2R losses of the reactor, that is copper losses, I2R losses of the reactor. So note that the loss characteristic of the TCSC shown in the A2 diagram correlates with its voltage compensation characteristic shown in the A1 diagram, that is these two. Okay, so that is the losses increase in proportion with the line current at the fixed maximum TCR condition angle obtained with the minimum delay angle, that is alpha C limited, and then the decline as the conduction angle is continuously decreasing with increasing. There is alpha is in between alpha C limited to pi by 2 to keep the capacitor voltage constant, that is below the maximum voltage constraint. Okay, then next, in the impedance compensation mode, the TCSC is applied to maintain the maximum rated compensating reactance at any time current up to the rated maximum. Okay, for this operating mode, the TCSC capacitor and thyristor control reactor, that is TCR, are chosen so that at alpha C limited, the maximum capacitor reactance can be maintained at and below the maximum rated line current as illustrated in the B1 diagram, that is this diagram B1. Next, the minimum capacitor compensating impedance the TCSC can provide is, of course, the impedance of the capacitor itself critically obtained at alpha is equal to 90 degrees, that is the non-conducting thyristor valve. So, and the loss versus line current characteristic for the operating mode is shown in the diagram, that is B2. It is for maximum and minimum capacitor compensating reactances. It is for maximum and minimum capacitor compensating reactances, that is this diagram B2. So here we have minimum and maximum capacitor reactances, that is XC minimum and XC maximum. Okay. So the reader is reminded again that the voltage and impedance compensation modes are interchangeable by control action. However, limitations imposed by component ratings may constrain the attainable range of the desired operating mode. Okay, next. So here I am taking for example the compensating voltage versus line current characteristic that is shown in the A1 diagram in the 6.20 can be transformed into compensating reactance versus line current characteristics, that is compensating voltage versus line current characteristics 6.20 is transformed into compensating reactance versus line current characteristic that is shown in the 6.21 diagram, that is this one. So this diagram is for the attainable compensating reactance versus line current characteristic of the TCSC corresponding to the voltage compensation mode, that is VA characteristics of the 6.20 A1 diagram. So in this one we have two regions, capacitor and inductive. So the inductive region is in the positive half cycle and the capacitor region is in for the negative direction. We have the XC maximum and XL maximum and XC minimum, XL minimum, and we have the capacitance, reactance of the TCSC scheme. Okay, like that we are taking. So from this one it can be observed in these figures that constant compensating voltage necessarily results in varying compensating impedance and vice versa, and constant impedance produces varying compensating voltage with changing line current. So this can be observed from those diagrams, and the maximum voltage and current limits are design values for which the thyristor valve, the reactor and capacitor banks are rated to meet the specific application requirements. Okay. And next, so the TCSC, like its future counterpart, the TSSC is usually required to have transient voltage and current ratings defined for specific time durations. So that is, the TCSC design is complicated by the fact that the internally generated harmonics aggravate the limit conditions. Next, the harmonic currents cause additional losses and corresponding temperature increase in both the thyristor valve and reactor. So the harmonic voltages they produce across the capacitor increases the crest voltage and the stress on the TCSC power component. So the effects of the harmonics must be taken into account under the worst case operating conditions to determine the necessary maximum voltage and current ratings of the major TCSC components to satisfy specified operating conditions. So outside these defined operating limits, the TCSC is protected against excessive voltage and current surges either by a shunt connected external production by the TCR itself in bypass operation. So the TCSC with partial conduction of the TCR injects the harmonic voltages into the line. So these harmonic voltages are caused by the TCR harmonic current which circulate through the series compensating capacitor. So the TCR as established in the previous chapter, that is the shunt compensation, generates all odd harmonics and the magnitudes of which are a function of the delay angle alpha. That is shown in the previous chapter, that is 5.10. And the harmonic voltages corresponding to these currents in TCSC circuits are clearly dependent on the impedance ratio of the TCR reacted to the series capacitor, that is XL by XC. So for XL by XC that is equal to 0.133. So that is used in the existing TCSC installations. The most important harmonic voltages, that is 3rd, 5th and 7th generated in the capacitor operating region are plotted against the line current I in figure 6.22, that is this one. Okay, this is the dominant harmonic voltages generated by the TCSC at an XL by XC ratio of 0.133. So here the casting diagram is drawn between the V pi by VC naught in percentages to the I value. In the percentage means 0 to 20% I am taking, and here I am taking 3rd, 5th and 7th harmonics of the capacitors, the TCSC. Okay. So in this one, the third, fifth, and seventh harmonics in the capacitive operating region are plotted against the line current I in figure, that is as percentage of the fundamental capacity, what is the DC naught with the PCR of and rated current. So for the plots shown, the TCSC is assumed to maintain the rated compensating voltage against varying line current as defined by the VA characteristics in the 6.20A1 diagram. Okay, so from these all, it can be observed that the magnitudes of the harmonic voltages rapidly decrease with frequency, and harmonics above the seventh are totally negligible. So the lower order harmonics, although appearing to have relatively higher magnitudes, may not contribute significantly to the existing harmonic line currents. So this is because these harmonics are substantially voltage sources, and the TCSC is usually applied to long, so high impedance lines in which the generated line current harmonics will be relatively low. So the figure 6.21, there is this one. So this 6.21 clearly indicates that. So clearly conveys that the TCSC does not have control below XC minimum. So the system frequency impedance of the capacitor to XL minimum, the system frequency impedance of the inductor. So if the TCSC is one large single unit, the uncontrolled capacitive band can be quite large. So a large uncontrolled band will make it difficult to use the TCSC for control of dynamic stability, that is polarization damping. So dividing this TCSC installation into several modules would enable sequential insertion of modules and narrow the uncontrolled band to small size. So it was established earlier that the GCSC controls the effective capacitor impedance from 0 to its system frequency impedance. So then it follows that in a modular TCSC arrangement, if one module is a GCSC, then the capacitor impedance may in principle be continuously controlled over its entire range. So this is the explanation for the variable impedance step series compensators, that is TCSC and TSSC. And now in the next class I am going to discuss remaining topics of this chapter. Okay, thank you for watching this video.